Hello, everyone. So I'm interested in figuring out how neural networks work and when do you expect them to work well. We have already statistical learning theory that tells us that simpler networks should work better. Unfortunately, the measures of complexity that we have now are dependent on architecture, and they tell us that these massively over-parameterized neural networks should really not work. So what I want to propose is a measure of complexity that takes the actual weights into account and the state of the neural network mapping. So the basic idea is that we presume that data input to the network lies on some manifold M, and the mapping, the actual mapping, depending on the weights of the network, produces some manifold N. And for any given point, input point, you can make a linear approximation of the output manifold, which is essentially a computation of a tangent space, and we treat it as a linear classifier or a pack concept. And if you take a number of input points, they form a bundle of those pack concepts, and those pack concepts span a certain space that we call a conceptual space. And here on the right, I'm showing you a 500 sample bundle example of just a visualization of that conceptual space. So on the top, I have VGG16 network trained on the MNIST and CIFAR10 data set. And on the bottom one, I have ResNet trained again on MNIST and CIFAR10 data sets. And as you can see, those conceptual spaces are quite different. Possibly some of them look simpler or not. So our measure of conceptual complexity is essentially based on some kind of entropy measure that takes into account the labels of the samples and tries to measure the complexity of that space. To put this idea through its paces, we did some empirical evaluations and essentially set up some experiment where we expect the complexity to behave in a certain way. On the left is the first experiment where we measure a VGG16 network trained on a CIFAR10 data set that's shown in blue versus the CIFAR10 data set with randomized labels. So the blue network generalizes, the orange network doesn't. And you can see the complexity, the conceptual complexity is data dependent. So on the bottom axis, you can measure it as the size of the bundle sample increases. So you can measure it over different bundle sizes. And as you can see, a network that generalizes well has certain conceptual complexity, but the one that doesn't with random labels, as the bundle size increases, the conceptual complexity increases, kind of suggesting that a random label network just has to memorize more diverse concepts, and it's more complex. There's more memorization. The second experiment in the middle is one where we try to figure out whether it transcends the architecture. So here we have 3 different networks of different size. The blue one is the smallest with about 2 million parameters, and the orange and green are about 30 million parameters, but the orange and green happen to train to a better minima. They're generalized better, and their conceptual complexity is smaller. Whereas if you were going by something like a VC dimension, you would have exactly opposite. So it's sort of conceptual complexity is sort of in this middle picture is correlated with the generalization rather than the network size. And to confirm that even further, we have the third experiment on the right. It's VGG16 trained. It's a CIFAR10 data set where we sort of add a confusion set to the training data to make it train worse and worse. And in the orange, I show the worse generalization. And in the blue, it's the conceptual complexity, which should be correlated. It's kind of hard to tell. We have a different experiment done on residual networks. And here on the right-hand side, you see that that correlation is pretty good. What do I want to do with it? There's a couple things that I can think of doing with this. The sort of most obvious thing is that whereas VC dimension sort of stays the same throughout the training, my conceptual complexity can change from epoch to epoch. So here I have a neural network that is trained over 100 epochs. Green line is the training error, orange line is the test error, and the blue line is the conceptual complexity, so we can see it changes. Where it kind of goes nuts is where the network fell over with Adam Optimizer. And so I'm thinking this the first thing to tackle is to do some kind of regularization where we can optimize the conceptual complexity directly. At the moment, I don't know how to do it because conceptual complexity is pretty hard to compute and it takes a lot of time. Thank you.